Shields up. In countless Star Trek episodes, this is the first order that Captain Kirk barks out to the crew, raising the force fields to protect the Starship Enterprise against enemy fire. So vital are force fields in Star Trek that the tide of the battle can be measured by how the force field is holding up. Whenever power is drained from the force fields, the Enterprise suffers more and more damaging blows to its hull, until finally surrender is inevitable. So what is a force field? In science fiction, it's deceptively simple. A thin, invisible yet impenetrable barrier able to deflect lasers and rockets alike. At first glance, a force field looks so easy that its creation as a battlefield shield seems imminent. One expects that any day some enterprising inventor will announce the discovery of a defensive force field. But the truth is far more complicated. In the same way that Edison's light bulb revolutionized modern civilization, a force field could profoundly affect every aspect of our lives. The military could use force fields to become invulnerable, creating an impenetrable shield against enemy missiles and bullets. Bridges, superhighways, and roads could in theory be built by simply pressing a button. Entire cities could sprout instantly in the desert, with skyscrapers made entirely of force fields. Force fields erected over cities could enable their inhabitants to modify the effects of their weather, high winds, blizzards, tornadoes at will. Cities could be built under the oceans within the safe canopy of a force field. Glass, steel, and mortar could be entirely replaced. Yet oddly enough, a force field is perhaps one of the most difficult devices to create in the laboratory. In fact, some physicists believe it might actually be impossible, without modifying its properties. Magnetic levitation in science fiction, force fields have another purpose besides deflecting ray gun blasts, and that is to serve as a platform to defy gravity. In the movie Back to the Future, Michael J. Fox rides a hoverboard, which resembles a skateboard except that it floats over the street. Such an anti-gravity device is impossible given the laws of physics as we know them today, as we will see in Chapter 10. But magnetically enhanced hoverboards and hovercars could become a reality in the future, giving us the ability to levitate large objects at will. In the future, if room temperature superconductors become a reality, one might be able to levitate objects using the power of magnetic force fields. If we place two bars magnets next to each other with north poles opposite each other, the two magnets repel each other. If we rotate the magnet, so that the north pole is close to the other south pole, then the two magnets attract each other. This same principle, that north poles repel each other, can be used to lift enormous weights off the ground. Already several nations are building advanced magnetic levitation trains, maglev trains, that hover just above the railroad tracks using ordinary magnets. Because they have zero friction, they can attain record-breaking speeds, floating over a cushion of air. In 1984, the world's first commercial automated maglev system began operation in the United Kingdom, running from Birmingham International Airport to the nearby Birmingham International Railway Station. Maglev trains have also been built in Germany, Japan, and Korea, although most of them have not been designed for high velocities. The first commercial maglev train operating at high velocities is the Initial Operating Segment, IOS, demonstration line in Shanghai, which travels at a top speed of 268 miles per hour. The Japanese maglev train in Yamanashi Prefecture attained a velocity of 361 miles per hour, even faster than the usual wheeled trains. But these maglev devices are extremely expensive. One way to increase efficiency would be to use superconductors, which lose all electrical resistance when they are cooled down to near absolute zero. Superconductivity was discovered in 1911 by Heike Onnes. If certain substances are cooled to below 20 R above absolute zero, all electrical resistance is lost. Usually when we cool down the temperature of a metal, its resistance decreases gradually. This is because random vibrations of the atom impede the flow of electrons in a wire. By reducing the temperature, these random motions are reduced, and hence electricity flows with less resistance. But much to Onnes's surprise, he found that the resistance of certain materials fell abruptly to zero at a critical temperature. Physicists immediately recognized the importance of this result. Power lines lose a significant amount of energy by transporting electricity across long distances. But if all resistance could be eliminated, electrical power could be transmitted almost for free. In fact, if electricity were made to circulate in a coil of wire, the electricity would circulate for millions of years, without any reduction in energy. Furthermore, magnets of incredible power could be made with little effort from these enormous electric currents. With these magnets, one could lift huge loads with ease. Despite all these miraculous powers, the problem with superconductivity is that it is very expensive to immerse large magnets in vats of supercooled liquid. Huge refrigeration plants are required to keep liquid supercooled, making superconducting magnets prohibitively expensive. But one day physicists may be able to create a room temperature superconductor, the holy grail of solid-state physicists. The invention of room temperature superconductors in the laboratory would spark a second industrial revolution. Powerful magnetic fields capable of lifting cars and trains would become so cheap that hover cars might become economically feasible. With room temperature superconductors, the fantastic flying cars seen in Back to the Future, Minority Report, and Star Wars might become a reality. In principle, one might be able to wear a belt made of superconducting magnets that would enable one to effortlessly levitate off the ground. With such a belt, one could fly in the air like Superman. Room temperature superconductors are so remarkable that they appear in numerous science fiction novels, such as the Ringworld series written by Larry Niven in 1970. For decades, physicists have searched for room temperature superconductors without success. It has been a tedious, hit-or-miss process, testing one material after another. But in 1986, a new class of substances called high-temperature superconductors was found that became superconductors at about 90 degrees above absolute zero, or 90 R, creating a sensation in the world of physics. The floodgates seemed to open. Month after month, physicists raced one another to break the next world's record for a superconductor. For a brief moment, it seemed as if the possibility of room temperature superconductors would leap off the pages of science fiction novels and into our living rooms. But after a few years of moving at breakneck speed, research in high-temperature superconductors began to slow down. At present, the world's record for a high-temperature superconductor is held by a substance called mercury thallium barium calcium copper oxide, which becomes superconducting at 138 R, minus 135 degrees Celsius. This relatively high temperature is still a long way from room temperature. But this 138 R record is still important. Nitrogen liquefies at 77 R, and liquid nitrogen costs about as much as ordinary milk. Hence, ordinary liquid nitrogen could be used to cool down these high-temperature superconductors rather cheaply. Of course, room temperature superconductors would need no cooling whatsoever. Embarrassingly enough, at present there is no theory explaining the properties of these high-temperature superconductors. In fact, a Nobel Prize is awaiting the enterprising physicist who can explain how high-temperature superconductors work. These high-temperature superconductors are made of atoms arranged in distinctive layers. Many physicists theorize that this layering of the ceramic material makes it possible for electrons to flow freely within each layer, creating a superconductor. But precisely how this is done is still a mystery. Because of this lack of knowledge, physicists unfortunately resort to a hit-or-miss procedure to search for new high-temperature superconductors. This means that the fabled room temperature superconductor may be discovered tomorrow, next year, or not at all. No one knows when, or if, such a substance will ever be found. But if room temperature superconductors are discovered, a tidal wave of commercial applications could be set off. Magnetic fields that are 1,000,000 times more powerful than the Earth's magnetic field, which is 0.5 Gauss, might become commonplace. One common property of superconductivity is called the Meissner effect. If you place a magnet above a superconductor, the magnet will levitate, as if held upward by some invisible force. The reason for the Meissner effect is that the magnet has the effect of creating a mirror image magnet within the superconductor, so that the original magnet and the mirror image magnet repel each other. Another way to see this is that magnetic fields cannot penetrate into a superconductor. Instead, magnetic fields are expelled. So if a magnet is held above a superconductor, its lines of force are expelled by the superconductor, and the lines of force then push the magnet upward, causing it to levitate. Using the Meissner effect, one can imagine a future in which the highways are made of these special ceramics. Then magnets placed in our belts or our tires could enable us to magically float to our destination, without any friction or energy loss. The Meissner effect works only on magnetic materials, such as metals. But it is also possible to use superconducting magnets to levitate non-magnetic materials, called paramagnets and diamagnets. These substances do not have magnetic properties of their own. They acquire their magnetic properties only in the presence of an external magnetic field. Paramagnets are attracted by an external magnet, while diamagnets are repelled by an external magnet. Water, for example, is a diamagnet. Since all living things are made of water, they can levitate in the presence of a powerful magnetic field. In a magnetic field of about 15 teslas, 30,000 times the Earth's field, scientists have levitated small animals, such as frogs. But if room temperature superconductors become a reality, it should be possible to levitate large non-magnetic objects as well, via their diamagnetic property. In conclusion, force fields as commonly described in science fiction do not fit the description of the four forces of the universe. Yet it may be possible to simulate many of the properties of force fields by using a multi-layered shield, consisting of plasma windows, laser curtains, carbon nanotubes, and photochromatics. But developing such a shield could be many decades, or even a century, away. And if room temperature superconductors can be found, one might be able to use powerful magnetic fields to levitate cars and trains and soar in the air, as in science fiction movies. Given these considerations, I would classify force fields as a Class 1 impossibility, that is, something that is impossible by today's technology, but possible, in modified form, within a century or so.